Okay. Are these lights going to be like this? Yeah. Okay. I'm going to be squinting. I see. Okay, I'll give it one more minute, maybe. All right, we still have some people filing in. Okay. All right, should I start? Yes. Okay. Is my mic on? Hello? Is my mic on? No. I don't think so. No. Hello, mic. My microphone. There it is. Okay, people are still filing in, but we need to get started. Just as a reminder, so Dave at the door there is collecting business cards or any other form of identification. We're going to do a raffle at the end. Given the turnout, your odds are pretty good. I think we're giving away a bunch of GPUs like this one. Cool. Okay, well, thank you for coming. My talk is on accelerating your VR applications with VRWorks. My name is Cebenoyan. I work at NVIDIA in the Developer Technology Group. And let's get started. So here's the talk overview, the things we're going to be talking about. The bulk of the talk is on the VRWorks features. So VRWorks is this software and hardware platform that we have for accelerating VR and optimizing, rendering, and other things that go into making the VR experience great on NVIDIA platforms. So I'm going to go into some features that optimize latency, features that optimize rendering performance, both steady-state rendering performance and latency, things that allow you to have higher quality or a better quality-speed trade-off given the VR context. And I'll also be talking a little bit about some new features that are actually not graphics related around audio and 360 video stitching that are super exciting and new additions to the VRWorks framework. And then I'll be going into a little bit about Unreal Engine 4 and Unity engine integrations that we've done, sort of what the status is, how they work, both to give you some sort of background on what features are available, when they're coming in those engines if you use them, and also to talk a little bit about what it takes to actually integrate some of the VRWorks features into a major engine in case, because these, as you'll see, some of these features are, have sort of complicated interactions with different things in the engine, and we'll talk a little bit about that and give you a better sense for how they work so you can take advantage of them better. And then we'll end with the neat video of our new VR game, VR Funhouse, and we'll talk a little bit about how that works. Okay, so the main thing, and this is sort of review for everyone in the audience at this point, of course, but it's sort of sets the stage for what the motivation is behind a lot of the things that we've added to VRWorks. And that is sort of how is VR rendering different than traditional 3D graphics rendering? There's a number of sort of characteristics, if you will, of VR rendering that make it a little bit different than traditional rendering. These are a few of them. One is that frame rate obviously matters a great deal. Frame rate's always mattered and will always matter. It matters on every possible platform that does real-time 3D rendering, but I think the stakes are higher in VR, right? You sort of have a 90 hertz refresh rate, and in the old non-VR case, you don't have, it's not such a big deal if you miss that refresh. But on VR platforms, as we all know, if you drop below 90 hertz, you have hitching that really hurts presence and really takes the user out of it. And so it's really important that you maintain that high frame rate. It's a lot more sort of do or die than it was on other non-VR platforms. And then combined with that is low latency. So traditionally, we sort of optimized for both latency and throughput. But throughput was probably, I mean frame rate. Throughput was probably king, it was probably priority number one. In the VR context, it's different. Latency is as important, if not more important, because obviously latency, it really impacts that feeling of presence, how quickly the user turns the headset and how quickly the scene responds really changes how they feel about whether or not they're actually immersed in that environment, right? So it's not enough just to optimize for frame rate. And some traditional optimizations that we do in graphics that optimize very much for frame rate turn out not to actually help latency all that much, and so they're not a great fit for VR. So we had to think about sort of how do we optimize for both of these things. The next characteristic of VR rendering is stereo rendering, right? So this is obvious, but it has some interesting ramifications, which is where you render two eyes, obviously. The characteristics there are that you're rendering two eyes from very similar viewpoints, but not exactly the same. So a lot of the same objects and characters and things in the scene are visible in both of those eyes, but they're in different positions. So they do require fundamentally different projections. But how can we take advantage of that to accelerate VR rendering? And then the last one that we think a lot about is lens distortion, right? Because of the nature of the actual devices and the lens that are on them, there's a distortion that's applied by those lenses to allow the user to focus at such a close distance comfortably. And that distortion has ramifications in how the rendering has to happen to make the view not appear distorted to the user. And so that changes the way that the rendering happens, and that ends up leading to optimizations that we can do to take advantage if we know the shape of that lens distortion that has to be applied before displaying to the user. We've thought a lot about how can we optimize that and make it so that we only render the pixels that are absolutely necessary given the characteristics of these lenses. So these are a few of the things that have informed the design of the VRWorks SDK. So here is the current state of the VRWorks SDK. The stuff most people think about with VRWorks, I think, is sort of on the left here, is the graphics-focused features, and we're going to talk a bit about those for sure. I'll go into what all those words, those names mean on the left there, but those are sort of 3D graphics rendering related features. Those are mostly things that need to be integrated directly into the game engine, the graphics engine of your renderer with sort of a deep integration, and those are the things that we've been working on integrating into the popular engines like Unreal Engine and Unity. The headset block, that's more for the headset developers, folks like Oculus, where they can take advantage of those features to improve the user experience for the end user who's actually using the VR platform. So those are not game developer or application developer visible typically. They're more for the headset guys. And then there's a bunch of other things that we're doing around physics. We'll talk a little bit about that. We have this new audio SDK that we're rolling out now for improving audio, which is very important. Again, to give that user a sense of presence in VR, and some features around video. So the first thing I'm going to quickly talk about here is context priority, which, like I said, is, like I said on the previous slide, is not a real end user or developer, application developer visible feature, but it is very important to the latency result that the user sees. And it has some, and it's something that we've improved a great deal in recent generations of our GPUs and in recent versions of VRWorks. And so I'm just going to talk a little bit about what the problem is there and what it is that we've done to improve it. So there's this concept of asynchronous time warp, which we saw Brendan talking about yesterday at the keynote. And the idea is that typically in a game, you render the frames as given from the camera pose as it is in some instant. You sort of sample the camera pose, you generate the visible geometry for that camera pose, you render it, and then you display it, right? The problem is there sort of at the point at which you sample the camera pose, which in the case of VR is the head pose, to the point where the user actually sees the results of the rendering from that point of view, there could be a significant amount of time there. And if and that time is latency, and that sort of messes with the user's feeling of being in the environment. And it also can possibly have problems with if you miss the refresh, then you're going to have some stutter, and the latency is going to be even greater. So the asynchronous time warp feature improves this dramatically by basically right before you display the frame to the user, it does a resampling of the head pose, and based on that resampling, saying, okay, where's the user looking now? Now, you've already done all the rendering. How can we warp that final image a little bit to match better with what the new head pose is? And that dramatically improves the perceived latency, and that can cover for a lot of slower rendering frames and things that can happen, which would normally hurt latency and hurt the experience. Async time warp really helps with that. Now, what does async time warp need, though? It needs, while the main rendering is happening, there's this sort of parallel async time warp context that's operating to actually interrupt the main rendering of the game and say, okay, we need to do this time warp because it looks like we're going to miss this refresh or something's, we need to do time warp, we've decided. The GPU is the thing that does the warp, right? So the GPU has to be interrupted in whatever work it's doing, and you have to now do this time warp operation, which is some standard 3D graphics sort of algorithm that does the time warp. And then you have to go back to what the GPU is doing. So this requires this ability to interrupt the GPU. And so in our latest graphics architecture, which we call Pascal, so the 1080 that I have here is a Pascal-based, all the 10 series GPUs. What it has is an improved version of what we call preemption, right? So in previous GPUs from NVIDIA, basically the preemption, the granularity at which you can interrupt the GPU and say, okay, stop what you're doing or pause what you're doing. Here's some new work to do, and then you need to go right back to what you were doing. That granularity was at sort of this command push buffer granularity. So what that means is like draw call granularity, right? Which works fine, but it's a little bit coarser than what you want, right? The finer you can make that, the lower latency you can have. And so in Pascal, now when you're rendering graphics, you can actually interrupt in the middle of a triangle the rendering. And so the final latency is much improved for operations like async time warp. So here's sort of a visualization of that. With Maxwell, which is the previous generation before Pascal and all previous generations. So Maxwell would be like the 9 series. The way it works would be like this. There's sort of this extra little buffering here between, so the GPU is rendering. There's a preemption request, which means, okay, we got to do time warp. That happens. There's sort of an extra little buffer of operations there that you have to leave because there could be work that's in front of you in the graphics queue, and it's very coarse. You don't know how long a draw call is going to take to complete and stuff like that. And so it ends up kind of looking like this, right? That there's this additional latency that you have to account for depending on how much work is in front of you. And so, so that sort of end-to-end latency, which is that bottom distance there, is some value. With something like Pascal, you can basically skip doing that buffering, right? So the end result is just, let's see if this works. PowerPoint may have crashed. All right, let's see if it works. It gave me a warning that it has stopped working. Wow. Have you guys ever had PowerPoint crash on you? In the middle of a presentation? I've given hundreds of presentations in my life, and this is officially the first time that's ever happened. In the middle of presentation mode, no less. Yeah, it's definitely quit. Wow. The folks wanted me to use a Mac for this, and I refused stubbornly. And this is karma, right? It looks like it's working now. We'll see. All right, well, there's a first time for everything. Okay, so the net result, sorry about that, guys, is that final latency, right? Let's go where we were before, right? That level of latency, lower latency. So it works better with async time warp because of this finer grained granularity that we have for preemption. Okay, so that's all good. Next thing I want to talk about is VRWorks audio. So a few slides on this. This is an upcoming SDK from us that's pretty neat. So we'll talk a little bit about why audio matters. What is the problem that's trying to be solved here? So there's multiple things to audio, right? There's synthesis, obviously, sort of the generation of sounds and the mixing of sounds and things like that in the environment, the creation of source sounds in a 3D environment. And then there's directional audio, which is sort of the main way that most audio is done in games, right? So when you have sort of positional audio in a game where sound is coming in, HRTF gets applied to determine the stereo result from some incoming sound from a certain direction, a certain level of attenuation and things like that. So it's very critical to making it feel like you're in a space, right? So what we typically don't do, though, is what we're calling on this slide propagation, which means sort of what, not just directional, if you're a ray tracing guy, not just, direct ray tracing, but multiple bounce ray tracing, right? So what that means is that the sound, not only do you model the sound coming directly from a sound source to your ears, but you also model the sound bouncing off of walls, being occluded by other objects in the scene, being muffled and doing multiple bounces potentially, depending not only on where the sound is, but also on the position of the geometry in the scene, the materials potentially that are on those geometries, right? We all know that, right? The acoustics of an environment are based not only on where the sound are coming from, my mouth right now and these speakers, but also on the materials, the space, the size of the space, the people sitting in the space, all kinds of things, right? And that's due to the propagation, that's due to the bouncing of the sound as it travels through this environment. And so that's sort of the next level of immersiveness for audio, right, is not just, actually I think Mike Abrash talked about this yesterday, right, where we have sort of a next level would be modeling not only direction, which is what we do today, but also the propagation and the bouncing. So one thing that we realized is that we've had this thing, this optics engine, this NVIDIA optics engine for ray tracing, which is primarily for graphics ray tracing, which is what we think about for ray tracing. But this problem is very similar to a ray tracing problem, right? So if we have a very efficient GPU-accelerated implementation of ray tracing, we ask, could we apply that to audio propagation and modeling? And it turns out we can. And so this is something that we're working on now, and it's sort of similar to path tracing, if you know the graphics algorithm path tracing, where we model the way that light travels through an environment. But this is applied to sound waves and sound waves. So we can do, when you GPU accelerate it, you can do dramatically larger arrays than you normally would be, right? Just like Mike Abrash said yesterday, there's performance is actually the problem with doing this properly. That's the only reason why. It's not that people don't necessarily know how to do this. It's just very computationally expensive to model not only the direct propagation of sound, but the bounced propagation of sound. And with multiple bounces every time, you end up having this sort of exponential increase in the amount of processing that you have to do. So GPUs are great at ray tracing, though. We've been doing that for years in graphics and in products like iRay and things like that we have. And so we applied it to audio in this upcoming VRWorks audio SDK that we have. So here's how it actually works and how you would use it in an application. So we basically have a bunch of inputs. Includes obviously the sound source, the location, the orientation of the sound, some environmental geometry that you want to use for modeling this propagation, right? It doesn't have to be the exact geometry that you would necessarily use for display. It's probably something coarser than that, but it doesn't have to be. And then also some material descriptions for the materials that are on that geometry so that the bouncing of the sound waves can actually model the way that it would be reflected given the materials and the environment. So then the VRWorks Audio SDK sort of takes over, does a bunch of processing there with the optics ray tracing engine underneath, and then hands back to you left and right ear audio outputs that you can use and mix, and it takes into account all the properties that you would expect and applies things like reverb and attenuation based on distance, and it's sort of the final audio result that you would expect. Okay, so this is coming soon. Not quite ready, but it's close for folks to use. Just want to give you a sense of that. So another thing also that's coming soon is this new 360 video stitching SDK that we've come up with in VRWorks. We call it VRWorks 360 Video. So the problem that this is trying to solve is everybody sort of understands, I think, in VR, the challenges of real-time rendering VR and displaying it to the user in a low latency way. So there's two main uses or consumption ways to consume VR content now, right? One is this sort of real-time model of the way the games work and things like that, where you have the final rendered result of a real-time interaction inside of a VR environment on a VR headset. The other is 360 videos, basically, right, where there's some captured visual, images of a scene in video, and then the user on the client side has a pretty thin client that's just sort of visualizing the results, right? But on the actual processing and encoding and decoding and all that side, that's actually quite computationally expensive. It's not super computationally expensive on the display side, because at that point, all the hard work has been done. But before you get to that point, right, you have to capture video from cameras, potentially 4K cameras, very high resolution, potentially lots of them. And then the actual work of taking those discrete camera inputs and turning it into one cohesive 360 panorama is quite computationally expensive if you want to do it really well and you have high resolution inputs, right? It involves, obviously decoding the encoded result from the cameras, doing some calibration, both sort of intrinsic and extrinsic calibration depending on the parameters of the camera and the poses of the camera so that you can make them all line up properly. Doing some equalization based on color balance and exposure and other things to make it seamless. Doing stitching at the borders to make it line up well and look seamless again. And then doing a re-encode at the end to then hand to either stream or store for later consumption. So that middle part, especially, the stitch part, is very computationally expensive. So this new VRWorks 360 Video SDK that we have handles all of those parts, right? So it offers both offline, so already pre-gathered video, and real time. We actually have a low latency video input path that we offer called GPU Direct, and it works with that for real time stitching from a camera rig. And all the phases in that middle area, from calibration to equalization to stitching to encode and decode, all of that stuff is GPU accelerated, so it's very fast and high quality. And then it sort of outputs some resulting panoramic output in some either equirectangular or a cube map type of projection, whatever the viewer application needs. So this is coming soon. Later this year, this will be available. So stay tuned and check out our VRWorks website for details on that. Okay, so now we're going to get into a little bit of the 3D graphics features. I don't know how much you guys are into 3D graphics nitty gritty, so I won't spend an enormous amount of time on this stuff, but I just wanted to talk a little bit about the features. So one is VR SLI. So SLI is something people who've been working with GPUs for 10 plus years now have been familiar with, and it's a great way to improve performance. And so it seemed like a natural fit, given the performance constraints of VR. Let's make sure we use VR. Make sure we apply SLI to VR. And it also seemed like there's sort of some natural synergy right there, right? We have two GPUs, we have two eyes. The common SLI case is two GPUs. You can do more, of course, but so how can we make this work and work efficiently? Well, this is sort of the way that normal SLI works, right? So when you just have like a non-VR display, a regular 2D display, and you're playing some game and you have two GPUs, this is the way the actual rendering happens, right? So the CPU submits work. So in this case, n means like frame n plus 1 is the next frame. Right, it submits work n. When it's done submitting that work n, the first GPU takes over and starts rendering that frame. And then the CPU goes to submitting work for n plus 1. That gets assigned to the next GPU. And then when those frames are done, the display takes over and displays it to the user. Right? So this is what we typically call alternate frame rendering. And this is the main way that SLI works in the normal desktop sort of or TV or any sort of 2D display case. So this works great, and it improves frame rate, and it can typically double frame rate for two GPUs depending on the situation. The problem here, though, is that while it doesn't make latency worse, it doesn't actually improve latency much, right? Because if you look at like all the green parts, for example, frame n gets displayed at the point where it would even if there was only one GPU, right? If you look at this diagram. And so while the total frame rate is doubled, the actual latency, the time from which the CPU starts submitting, presumably that's when the head pose was taken in VR, to the point where the user actually sees that updated frame is actually not any faster. So not ideal for VR. So what we do in VR SLI instead of alternating frames, so in that previous graph when we said frame n, what we really meant is like left and right eye for frame n, and then n+1 would be left and right eye for frame n+1. What we instead do is we just split it up, right? This is sort of natural. CPU presents or submits frame n, and then what we do is we have the left eye part of frame n rendering go to one GPU, the right eye go to the next GPU, then we display it right away. All right, so as you can see there, the latency is dramatically lower. And this works because of the stereo rendering that we talked about, right? If they were completely arbitrary viewports, this would not work as well. But because there's a lot of commonality between the two eyes, this is sort of a very natural fit for the way that VR stereo rendering works. So you get an improvement in latency, and you do actually also get an improvement in frame rate as well in this case. So this is the optimal situation for the VR SLI case. So in terms of how our API actually works, there's two different modes. So the typical thing what you would do is you would do like left eye rendering to one GPU, right? So you send all the rendering commands to one GPU, and all the rendering commands to the other GPU for the right eye, right? This is not optimal, but this is there available, and all you do, we have these APIs. The right one is OpenGL, the left one is Direct3D, where basically you can just say, now I'm using GPU 0, and now I'm using GPU 1, and all the commands that come after that go to that GPU or the other GPU. And what it can also do is say, send all the commands that I'm now sending to both GPUs, because there's some stuff, if you have the stereo case, there's some stuff in the scene like shadow maps and other sort of view-independent things that are probably going to be shared between the two eyes, right? And typically what you want to do in that case is you just want to render those on both eyes. So this makes it so you don't get perfect scaling in terms of performance scaling, but the API allows that, right? So you can say for this rendering, render it to both eyes, because both eyes are going to have the same shadow maps they're going to have to use for making the final lit result. But for the stuff, for the main geometry rendering, send the left eye's geometry to left eye, right eye's geometry to right eye. So this works fine. The problem with this is that you're sending all of your commands to the GPU twice, right? Once for the left eye, once for the right eye. So the question is, can we do better than that? And it turns out we can. So we have, so there's this concept of sort of, okay, can we broadcast the commands, right? So instead of sending it to the left eye and the right, and then resubmitting for the right eye, can we instead do one set of commands and have the GPU and the driver automatically send commands to the left eye and the right eye? Well, it turns out you can, because there is so much overlap between the command streams here. So the way that API works is that basically we have these. This left one is Direct3D, right one is OpenGL. They're just there for sort of like reference. The idea, though, is basically for things that are different between the left eye and the right eye. For example, the camera matrices are slightly different, right? They're offset by a couple of inches, and things like that. Those things we have the separate API that allows you to say, okay, set the state for the left eye, and simultaneously set the separate state for the right eye, but send the rendering command only one time, right? So you set the left eye state and the right eye state in constant buffers with one call to the API. But then when you say like draw, you only have to say draw once, and then under the hood, the driver and the hardware automatically selects the right constants depending on which eye is currently being rendered, right? So it'll automatically do the work of setting the left eye constants, which you specified in that call, sending having those set for the left eye and having the other one set for the right eye, and broadcasting all the commands. So this is much better in terms of overhead, CPU overhead. So this is the more efficient path. It can just be sometimes, depending on engine design, a little bit more tricky to implement, and so we have both of these models. The other thing that you often have to do is do data transfer between the two GPUs in the SLI case. So we have APIs for that as well. Like if there's some shared resource or something that needs to exist on both GPUs, you can do asynchronous copies using these APIs. I'm not going to go through every parameter here. Don't worry. Okay. We also do have now, and this is brand new, which is why I put it in here, an NVIDIA extension for accelerating a lot of this SLI stuff in OpenGL in exactly the same way. In fact, significantly better than what we have. What we used to have in D3D, because it has some additional flexibility here. But it's called NVGPU Multicast, so if you're interested in that, you can just Google that and find the extension spec. But it supports all the things I've talked about. So we have full support now in D3D and OpenGL for all of the functionality. Okay, so that's kind of a whirlwind VR SLI. It's cool. If you want to learn more about this stuff, you can go to our GameWorks site, check out VRWorks, and there's a bunch of documentation and sample code and stuff on there for this. Next thing I want to talk about is multi-resolution shading, which is sort of kind of a baby step towards foveated rendering. Right? So this is using that final thing, characteristic of VR that I talked about, which is the distortion that's introduced by the optics that are in the headset. Right? These optics are there to allow you to focus close, and because of this distortion, it has impacts in the way you render. And the question is, can we take advantage of those impacts? So here's what actually ends up happening, right? So the actual the image that's sitting in the actual frame buffer that's sent to the display, the headset display, actually looks like something on the left there. And then the optics get applied, by physics. They're just sitting there, right? The light goes through those lenses, and then what you actually end up seeing is something that looks like this. Now, this doesn't actually exist anywhere except in your mind. It just ends up looking that way because that left image has been generated, especially knowing what the characteristics of the optics of the headset are, right? So this is how it works, and so now we don't have actual support for rendering in this weird way, right? All GPUs render in a standard sort of perspective projection method that we've always used. There's no native hardware support for rendering in some distorted, warped space that matches directly the characteristics of the lens. And so what we do instead is that the game engine sort of renders this image on the left just like it normally would with a regular 2D display. And then there's a post-processing, a complex post-processing shader that gets applied to do to sort of distort it in a way that accounts for the distortion that's going to be applied by the optics, right? So there's this post-pass that happens that does this distortion, and then that's actually what ends up getting displayed and then warped by the optics. So one of the things that we noticed with this is that, so if you have this is a visualization of sort of what happens and how the different regions of the actual image get warped by this resampling warp that happens. Right, so something in the center, so that ellipse that we have in the center there, that's pretty much, that ends up being the same, right? It's not really modified much by this distortion. But that rectangle in the periphery gets warped a dramatic amount. So obviously it changes and is no longer a rectangle, but it also, importantly, shrinks in size, right? So the total area in terms of pixels covered is much less in this case, right? Maybe as little as half as much as it was on the left image. So what you did is you sort of rendered all of these expensive pixels, right? We know how expensive pixel shaders are in games. There's a lot of complex lighting effects and shadowing effects and all these things that are happening. And then you ended up, by virtue of this resampling that has to happen for the optics, throwing away a bunch of that work. So that doesn't seem optimal, right? So the first thing we came up with is what we're calling multi-resolution shading. We've been shipping this for a little over a year now. It started with the Maxwell family. And that basically, there's functionality in Direct 3D and actually all the major APIs, which allows you to, using a geometry shader, send your geometry to different viewports, more than one viewport, right? Traditionally, there's only one viewport. But using this functionality, you can actually send your geometry to multiple viewports. So what we do is we dice up the screen into, you could choose any configuration. And what we've sort of settled on as a good trade-off is a 3x3 configuration. And but the sizes of these viewports are completely up to the user, right? You can set it however you want. You can change it, and you should probably change it depending on the game, the nature of the game, where interesting stuff tends to sit in your game and things like that. And then what you do is you sort of squeeze in the sides viewports are made much smaller than the center viewport, and that scaling is up to you. And the end result here is that you end up rendering fewer pixels, and the number of pixels you render in the periphery lines up better with the number of pixels that end up actually getting seen by the user, right? So you have a better match there, so you're not over-rendering, and you're not paying this expensive cost that doesn't end up actually providing any value for the end user. Now, one of the problems there, though, is that, like I said, you use a geometry shader to do this sort of sending of triangles to different viewports. Now, turning the geometry shader on has a cost to it, right? And depending on this logic that you're doing to determine which viewport that a triangle falls into and things like that, it could be a significant cost. And so you end up having the situation where in an effort to optimize, you pay some cost, so you're kind of in the hole to start with, and then you got to dig yourself out of this hole by saving it by rendering fewer pixels. So sometimes that ends up helping your performance, and sometimes it doesn't, which is always kind of a bad optimization when it only helps some of the time, because then you can't just turn it on all the time, right? So what we did starting in the Maxwell generation is that we added support for sort of special casing this functionality specifically needed for this feature in the hardware. So what we have now is this fast viewport broadcast, where if you have a special kind of geometry shader, a geometry shader that does nothing more than, or very little more than just taking in this input triangle and then routing it to a viewport. It's not doing any complicated, generation of new geometry or things like that. It's just a very simple type of geometry shader that just does this. It's a super fast path through the hardware. And so you end up having it, you don't have this characteristic where you start in the hole performance-wise, and then you have to dig yourself out of it. It sort of starts neutral. It doesn't hurt performance at all. And then you get all the benefits then of rendering fewer pixels. So Maxwell and beyond. So Maxwell GPUs, which is the 900 series of GPUs, and obviously the new Pascal series, the 10 series of GPUs, all support this feature. So in the Pascal generation of GPUs, that we launched earlier this year, we also added an advancement to this technique, right? So the multi-resolution shading is really neat and helps a lot on performance, but it's kind of a coarse approximation to what the lens is really doing, right? The lens has this complex warp that it applies to the image, and so it's not just simply, this is not this piecewise thing where you have the center is a given resolution and the periphery is just suddenly much lower resolution. It's not like that. It's a smooth sort of gradation that the optics would ideally like you to render in, right? But that's even more complicated. And so for us to be able to take a big step towards approximating the lens distortion in terms of rendering, we had to add actual hardware support for this. So we call this lens match shading. And what it does is it basically it breaks up the viewports into things that are no longer sort of planar and with a fixed resolution, but instead has this sort of warped resolution that matches the lens optics much better. Here's another visualization of it. And I'm going to have a little demo that shows a visualization of this as well. But in this case, so unlike the multi-res one where we had seen before, where we had those 9 viewports, we have 4 viewports, and they're warped in this way. So to actually render in this warped way and then unwarp it actually requires some hardware support. So we've added a bunch of support in the Pascal generation to do this. But what you end up having is a closer match between what you render and what the optics would have liked you to render, right? And so what we're trying to get to is sort of a perfect match where there's not a single pixel wasted, and you just render all the pixels you render and pay all that shading cost for exactly match up with what the user sees and gets value from. Right. So this is a great optimization. It ends up improving quality and improving performance, and all of these things are flexible, right? In the case of multi-resolution shading and in lens match shading, the amount of distortion, the amount of decrease of rendering in the periphery and stuff, that's all flexible, right? The hardware and software is flexible, and so you can set it to whatever you want. And different games, I think, depending on the way that they render, I think would have different trade-offs that they would make in this case, and depending on the gameplay. You could imagine a first-person shooter type game maybe where users focus very much on the center of the screen, could have more aggressive settings here. Something that's maybe has more stuff in the periphery that's important, maybe would have more conservative settings. But we also, in the code that we have on the web, we have settings that are just sort of, I would say, optimal in the sense that we will guarantee that it does not make the image quality any worse. There's a setting for that. It still saves performance though, because it still reduces the rendering costs, but it's guaranteed to not make the rendering any worse at all, even in the periphery. And then we have more aggressive settings you can also use if you can afford a little bit of reduction in rendering quality in the periphery. So it's all up to you. Another feature we added in the Pascal generation is based on this observation of how traditional stereo rendering works, right? Where we have this left and right eye passes that are comically separate in this case, but they're rendering 2 different views, but they're of the same geometry. And so we thought, can we actually accelerate this case on the geometry side? Because one of the things that this requires is 2 renderings of the geometry, right? So you end up paying the cost of transforming and lighting and fetching indices and fetching geometry and all that stuff twice. So could we optimize this? So what we came up with this is this new feature called single pass stereo. And you see it here sort of visualized along with lens match shading, where what you do is you actually only submit the geometry one time, and the actual hardware only does all of the geometry calculations for that geometry one time. So it's not just a software feature. It's actually a hardware feature which has the hardware geometry pipeline only getting run once for both eyes. And then after the geometry part of the pipeline, you end up having to rasterize 2 different views, of course, but it saves all that work before rasterization. So it's, especially if you have a lot of geometry in your scene, it can be a dramatic speed up. All right, let me show like a little visualization here. We're coming to the demo part of the talk, so this will be less talking, more demo. So here's sort of a visualization, and let me actually stop the presentation. There's no image up there. Can we get an image up there? Hello, AV folks? This part is hard, right? This part is, can we get an image up here?
If you were relying on PowerPoint to have a separate second smart screen, you might have to pull the video.
No, this was working like 5 minutes before you guys walked in. Everything's black. Are you guys getting a signal right there? Are you getting a signal now? Yes? So now if I escape out of this, you get nothing? But PowerPoint is not even doing anything right now. Okay, that gives me a hint. All right. It's weird, this was just working. This should work? All right, we'll have to go with that. Okay, so we'll see what happens with later demos. All right, so this shows you the stereo rendering here, right? I'll try to run this without actually seeing it on my laptop. So one of the things that, like we said, we need a lens. So we can have a visualization of what happens when you apply a lens there. And one thing you'll notice, like we talked about, is that so if we didn't do any pre-distortion, which we're not doing in this case, the 2 boxes in the bottom here is sort of what the user sees. And you see you get this kind of nasty stretching, as you would expect, as the optics distort the image, right? So we don't want that. So what we do instead is we do this pre-correction. And so that gets rid of that distortion that you see. But now you can see the final rendered image, or the image that has to be rendered by the GPU while it's actually rendering the scene. You're wasting all that space, right? And so what we can see here is there's a visualization of what we do in the lens match shading case, where we actually warp the rendering, so we end up having 4 projections which better map the actual distortion that the lens actually applies. And so you end up having a much closer approximation to the actual final rendered image, right? So if we see here, you have sort of that is what the optimal rendered image would look like in the case where you have lens correction. And the 4 projections that you do per eye closely match that final image. So that's just a quick visualization that we have here. Let me run through this. Okay, so now we're going to talk about the engine stuff real quick. And I'm going to go through this pretty quickly since we're running out of time. So for Unity, I'm happy to announce that it's coming as a Unity plugin. It's a plugin, so it should be pretty straightforward for licensees to take advantage of. We're going to be supporting multi-res and single pass stereo and lens match shading in that initial implementation. So a lot of goodness there. And it will support most of the basic post-processing features. I know a lot of VR games are not using a ton of post-processing, but most of it's supported there. And it is only working for the forward rendering path in Unity. So this is, we're not ready to say exactly when this is going to be available, but it's coming soon. So on UE4, we have a lot more sort of currently available that you guys can get. I'll talk a little bit about that. So as of a week or two ago, we actually have an implementation with the full VRWorks suite. So basically everything I've talked about here, I mean all the graphics rendering features I've talked about here are available currently on GitHub. So if you're a licensee of UE4 and you need to log in to GitHub with your account, they can access UE4. So that link will work. And it gives you VR SLI, multi-resolution shading, single-pass stereo, lens match shading, all against 4.12. The 4.13 will be ready any day now. So hang tight. Or if you want to do the merge yourself, feel free. For multi-resolution by itself, we actually have a bunch of different, we've been doing this for a while, as you can see. So all the way going back to 4.10, we have full multi-res implementations. And over time, we've sort of improved the integration and made it more robust and higher performance. But all of those, we have that for 4.13 as well right now. So you can go grab that right now. It's full source code. When we started this with 4.10, one of the things we noticed is that the post-processing shaders were taking a great deal of the time. And I'm going to talk a little bit more about that. But for that reason, every single possible post-pass isn't supported with multi-resolution shading or with lens match shading at this time. So we support all the common ones, though, like temporal AA and bloom and tone mapping and things that everybody needs. This was in the 4.10 integration. In 4.11 and beyond, we added a bunch more useful ones. So we do support things like SSAO and screen space reflections, which were pretty challenging to get working. It works with instant stereo on or off. So that's totally orthogonal to the implementation we have. And it provides pretty dramatic speed-ups, right? So on sort of like stock UE4 content, like Infiltrator, you're talking about 30 to 40% speed-ups. We'll talk about VR Funhouse in a bit, where we're seeing speed-ups similar to that. And I'm going to show you guys a demo where you can see some speed-ups like that. And the actual way that the integration works, it's not a plug-in. So it's a little bit, it requires an actual code merge. It's a direct engine integration. And this is true, actually, of all these rendering features that we've done: single-pass stereo, lens match shading, and multi-res. And it sort of touches the RHI at the level of adding support for multiple viewports. Like I said, all of these techniques require rendering to multiple viewports and using geometry shaders to render to multiple viewports. So that support's been added. And then it touches a bunch of post-processing shaders, which I'll talk about in a second. All right, so there's basically two different types of rendering passes. And this applies to any engine, but definitely applies to Unreal Engine, where there's sort of the part of the engine where you render geometry. So in that case, what you have to do is add this fast geometry shader like we talked about, set all these viewports. And that applies to a bunch of different rendering passes in Unreal Engine. This is sort of Unreal Engine speak. And then at the end of the pipeline, when we're doing the post-processing, now that you have this warped image, you have to account for that warp in doing the post-processing, right? If you're going to do a bloom shader, where you're doing the bloom, if it falls into one of the squished parts of the viewport, you have to account for that. Otherwise, your bloom will look wrong, right? And so we've done the work for most of the common post-processing passes. In the case of the post-processing passes, there's sort of two common cases that you end up doing, and this is what we've seen. If you look at the code on GitHub, you'll see this work where there's two different sort of broad categories of type of algorithm that you end up having to account for. One is things like any of the deferred shading pieces where you have to reconstruct some sort of 3D position given a 2D position and a depth. That is going to depend on how was that projection generated and where in the viewport were you. So we have to account for that. And then you have this problem with some of these things that have large filter kernels, and it can get a little tricky because if you're doing some large bloom, some of the samples of that bloom can fall in one viewport, some can fall in a different viewport, and you have to account for the different pixel densities in each of those viewports and stuff. Anyway, this is more if you plan on doing it yourself. So maybe I'm just telling you this is hard work. So like this is, for example, the UV remapping I'm talking about, right? So if like you're sampling that column there, you have to make sure you're still sampling that exact column instead of just stupidly sort of using the same texture coordinates. So you basically end up having to change your UVs when you're doing your post-process passes. This is how it actually looks in code. Fun, we have code in the slide. So this is like UE4 code for doing shadow, reconstructing the position to do shadow mapping. And what you end up having to do is we basically change it to this. So with two things that we've added here, one is that we have this multi-res remapping line that takes the coordinates, the UV coordinates, remaps them for multi-res, and then we just use that UV when we're doing all the math in the future. So this is a pretty simple example. Some of them are more complicated than this, but in general, that's what you end up doing. You know, a place where that UV is referenced, you end up having to do this remapping of the UV to get the multi-res adjusted UV, and then feed that into the rest of the algorithm. All right. Now we're going to try to do a demo. I'm a little scared. This is full screen, so maybe full screen. We'll do something cool. That's not promising. Someone needs to explain to me why this worked 15 minutes before, and now it's not working. Yeah. So if I make this duplicate, which I could have sworn we did. Let's try that. Yes. Okay. So this is some stock content from UE4 called Shooter Game. I'll let the match start here, and we can visualize how multi-res actually, what the final result is. So I'll pull up stat FPS, which gives you a frame rate counter up there. And then I'll go ahead and enable multi-res. You'll see the frame rate go up from 80-something to 115 frames per second here. And you can see sort of in the edges, you would expect it to be much lower quality, or see a seam or something like that, and you really don't see anything. So we have a visualization here. This is not a seam. This is a visualization that we added so you can actually see what it's doing. So this is the 3x3 that we have for the multi-res viewports. So this is after we've sort of unwarped them, right? That's why they look kind of the same size. But you can see here, this is with no multi-res. This is with the first level, sort of a conservative setting. This is with a more aggressive setting. You see the frame rate go up, you know, from 80 something to all the way up to 120, almost 119. So really big speed up. But if you take out these intentionally introduced borders, there's no seam. There's nothing at all, even though you're rendering that periphery in much lower res, and you know, you've gotten a 30–40% speed up, right? I have actually a build on here that intentionally has a bug in it to just give you an idea of the sorts of things you might see if there is a problem with multi-res. So this is before we had fixed the SSAO shaders. This is kind of an old build. So the version on GitHub now doesn't have this artifact, but I think it's instructive because what you can see is I turn on multi-res, and we can see that it's on with this mode. If you look closely at some of these white walls, you'll see a seam. Right? Now, actually, the previous thing I showed you also had this bug, and you couldn't see it because it really is content dependent, right? But in this case, SSAO was not implemented for multi-res at all, and so especially on white walls, you get this artifact, right? So like I said, this is fixed right now, but it gives you an idea of the kinds of things you can see. It can be kind of subtle, so you can think it's working, and it's really not. I mean, even if I turn around this way, you really can't see a seam. At least I can't. But there are certain viewpoints where it's much more obvious. You also have this behavior at the top of the screen there where this SSAO kind of cuts out a little bit, but it's subtle. It can be subtle. But in this one as well, frame rate wise, you know, you go from, let's pick a not quite so fast viewport, like 80 something frames per second, 87 to 130 with you know, almost no degradation in image quality, so it's pretty awesome. Obviously, this depends on your content being GPU bound and things like that, right? So this content on this laptop, I have a 970. Let's see if this still works. The slides now won't work. All right, everything works. Cool. Obviously, like I said, it's dependent on being GPU bound, right? But for content that is GPU bound, especially fragment shader, you know, pixel shader bound, it can be a huge speed up. And that's totally up to you, right? It's totally flexible. You can set the scaling however you want and get more or less speed up and more or less aggressive settings depending on what you want. So the last thing I'm going to show you guys is VR Funhouse, which we released earlier this summer, which is a VR game from NVIDIA, totally free online. You can get it right now. And we also announced this week that it's coming to Oculus Touch. So it's very exciting. So it'll be available on all the VR platforms now. And you know, Funhouse is something that started off for us as kind of a demo to show what could be done. Right? There was this, I think everyone felt like we had this really cool technology that we'd built that would be really compelling, especially in VR, because it improves the, there's a richness to the environment that can be appreciated in VR even better than it can be, outside of VR. Things with all the physics technology that we've built where things interact correctly depending on how you interact with it. We all felt like in VR this would be even more exciting, right? And so I started working on this and then realized, hey, this could actually be a really neat VR game. And it turned out to be, I think, even more successful than any of us hoped for. It really is a lot of fun. If you haven't tried it, you should definitely try it. But it integrates a bunch of different GameWorks features that we have. These are all sort of the names for them. A lot of it's sort of physics-based because it's a carnival type of game where you have all these fun carnival games and things break and blow up and you shoot bows and arrows with fire on them. And so there's a lot of opportunity for fluid simulation and rigid body simulation and destruction and hair simulation. We have hair actually on these like whack-a-mole things, or these punching guy things and the whack-a-mole things. So this sort of brings together a lot of the stuff we've been working on for years. And it also has some of the VRWorks features we talked about, like multi-resolution shading and VR SLI. Multi-resolution shading is in there, like I said, so it gives you 30% speed up. And that's in the version that's on the web right now. And VR SLI is also on there. So we really needed it for some of these high-end effects that we were adding. Right? It really made the difference between being playable and being super immersive and it being a little bit too low frame rate. So this really saved us, actually. So you can check that out. Right now, we also very recently released a mod pack that you can download. So this is using Unreal Engine. And that was actually one of the advantages of using a standard engine, since we've done all this work with all these GameWorks integrations of PhysX and all the physics features and destruction and flow and flex and VRWorks. It was very easy for this group of really mainly artists and designers at NVIDIA. It didn't require a ton of programming work because all this stuff was already integrated into the engine. And what we've done, sort of in that vein now, is release a mod kit that you can get through the Epic Games launcher, which allows people with no programming at all, just modders, to do cool modifications. We released some mods ourselves to kind of get people started, which is super fun. And we also have the full source code on GitHub. If you have a UE4 license, because it is UE4 source code, you can get that just for free on GitHub right now. So depending on what level of modding you want to do, you can do sort of a traditional mod, doesn't require programming, just requires knowledge with Unreal Engine, and you can do some programming through blueprints and things like that. Or you can go ahead and access the full source code and see how we did things. So I'm going to play the trailer now. Yeah, it's super fun. If you haven't tried it, you should try it. It really is a lot of fun.